Tetris is the second best-selling video game of all time, with 520 million sales and 220 official versions released. However, the most popular version to this day remains the Nintendo Game Boy version. That was the goal of my project, to create a Game Boy-like handheld Tetris console. Here is a high-level overview of my design. I determined that I would need 3 major subsystems: a 6-button user interface, an LCD, and a piezo buzzer for background music and sound effects. Let's go over the final implementation now. The whole thing runs on a 9-volt battery, which is connected to a buck converter to step down to 5 volts. This feeds the 3.3-volt voltage regulator over a disconnectable jumper for debugging. The regulator has a 0.1 microfarad capacitor on the input and a 10 microfarad capacitor on the output for decoupling. This board primarily hosts the 8051 microcontroller, which is serviced by a 4.7 microfarad decoupling capacitor, an oscillator circuit, and a reset circuit to hold reset high until the oscillator is stable. I discovered that this was necessary once the electrical characteristics of the circuit were changed by adding the piezo buzzer. The button board connects to this one through a 7-pin interface, one for each button and a ground. There are also 2 structural pins. Each button will ground its respective line when pressed. These lines are tied to port 1 on the 8051 from pins 1 to 6. Pin 0 is the timer 2 output, so it is reserved for the piezo signal. In software, port 1 is pulled each frame and compared to the state from the last frame to determine which buttons have been pressed. Most of the wiring is dedicated to the LCD. The LCD runs at 3.3 volts, so all 11 signals must run through these bidirectional logic level changers. Data lines 0 through 8 are tied to port 0, read and write are tied to read and write on the microcontroller, and the data command select line runs to address 8 on port 2. This is to facilitate the memory map. Any address past 3 FF hex will exceed the internal 1 kilobyte of expanded RAM and interface over port 0. Address 8, the lowest address line that doesn't require a latch, corresponds to a change in 2 to the 8 or 100 hex. Thus, 400 and 500 hex will work as our command and data addresses respectively. For example, here's the function that most of the draw calls use. It uses bit shifting and masking to either fill, erase, or invert a given rectangle on the screen. The 11 LCD signals leave 1 pin left over on the 3 4-pin level changers, which is perfect for the 3.3 volt piezo buzzer. The aforementioned timer 2 pin, P1.0, runs through the level changer and then directly to the piezo. In software, this means we just need timer 2 to generate a square wave of a certain frequency, which it can do in programmable clockout mode. The frequency is determined by the values in the reload registers and are related by this formula. Timer 2 reload values can be pre-computed for all of the notes that need to be played, which is done by this Python utility that reads a MIDI file and creates a list of timer 2 reload values. I also manually pre-computed values for certain notes that are used for sound effects. To play back music, timer 0 is used in 16-bit mode to step through the list. To play sound effects, I used a short circular cue to which the game logic functions and cue successive notes for sound effects. Again, timer 0 regulates the playback. Putting it all back together, here's how it works. All the main menu graphics, which are copied from the Game Boy menu screen, I drew in a pixel art editor, which already supported outputting to a C file. I did have to modify it to be bit-packed black and white data. The main menu will also cycle through an AABA form of the Tetris theme song. Most of the game logic is pretty typical. There are a few interesting engineering challenges, though. First, all of the tetramino data is bit-packed to save memory. Note that amino is the name for one of the cells that comprises a tetramino. You can see that I am storing width, height, and mino x and y coordinates, each of which is a 2-bit value. The width and height can fit into a byte per tetramino, since the width and height are the same for alternating rotations. For mino locations, it's just 4 bits per mino per rotation, or 64 bits per tetramino. The other challenge is random piece generation. Any kind of pseudo-random generation requires a seed for the number generator, which is usually initialized with the system time on other computers. However, that is unavailable on the 8051. I solved this problem by using the delay between startup and when the player hits the start button as a seed. It's only incrementing an 8-bit integer though, so it can only technically play 256 different possible games of Tetris. Coming back to the gameplay, you can hear that there is a different beep for different inputs and a longer sound for events like line clears, Tetrises, and level up. Often these happen simultaneously, like when leveling up after getting a Tetris. However, there is never any clipping or cutting off since all of the effects go into the queue. This makes for a longer, rapid succession of tones on one of these events, which I find rather satisfying. My project is complete. It met all of its design goals, and the only issue is a minor graphical bug which you might have noticed, in the form of small artifacts left behind by moving objects. Since it's infrequent, doesn't show up on a logic analyzer, and gets erased every time a line is cleared, it was a low priority to fix, and I ran out of time to chase it further. Overall, I'm extremely happy with the final product. Thanks for listening.